All right, now we're going to look at another example of what can happen when sound waves combine. Remember, we call it interference when more than one wave is existing in the same place at the same time. One example of interference with sound waves is when you have sound coming from two separate sources and they overlap and meet at various points in the room. For example, if you have a concert hall or an auditorium where you have two speakers, one on either side of the stage, the sound waves from one speaker will spread out to fill up the room, and the sounds from the other speaker will spread out to fill up the room, and they're going to overlap and interfere. Now, depending on how far the waves from one speaker travel compared to the distance that the wave from the other speaker travels, you might end up with either constructive or destructive interference. So that means that some spots in the room are going to be quieter while other areas are going to be louder. This spot, these lines here represent the crests. I've drawn dotted lines to represent the crests, or actually compression since we're talking about sound waves, longitudinal waves. The dotted lines represent the compressions from this speaker. The solid lines represent the compressions from this speaker. So here, this point is receiving a crest from one source and a crest from the other. So right here, we have constructive interference. So somebody sitting there would hear a louder sound. I can draw that here. Here we're looking at all the waves spreading out to fill up the room. Here's that same point from the same two speakers. So here's just the wave traveling to that point, and it reaches this point, let's say, at a crest, and the wave from the other speaker also reaches as a crest. That's a pretty terrible drawing, but hopefully you get the idea. They travel either the same distance to get to this point, so they arrive in phase with each other, or they're traveling some multiple. The difference in the path length is some multiple of a wavelength, so that if one wave is lagged behind the other, it's lagged by one full wave, so it still reaches that point in the same phase as the wave from the other source. This point is getting the crest from one source, but the trough from the other. It's between two compressions. So here, the path difference is such that one wave arrives at a crest, while the other wave arrives as a trough. So here we'd have constructive interference, here we'd have destructive interference. This would be a dead spot. It seemed quieter there. Now, the only way you can tell that this is happening is if you were to move around the room and listen for subtle increases and decreases in volume. And it may not be something that's terribly noticeable. For example, here I'm assuming that only one frequency is coming from these two speakers. Well, if you're going to see a concert in an auditorium or a concert hall, there's going to be multiple frequencies coming from these two speakers. So there's going to be multiple wavelengths. That means that one spot may be a constructive interference for some wavelengths, but destructive interference for other wavelengths. So it's not like if you're sitting in a spot of destructive interference, you wouldn't be able to hear anything. It just means that the balance of the sound may be off. Perhaps where you're sitting, the lower frequencies are at destructive interference, so you can't hear the drums or the bass as well. But the higher frequencies are at a point of constructive interference. So the vocals and the guitar seem too loud, where somebody sitting somewhere else might be the exact opposite. Maybe they're sitting in a spot where the lower frequencies are experiencing constructive interference, and to them the bass and the drums seem too loud and they can't hear the guitar and the vocals. So this can affect the acoustics of a room. This kind of interference pattern is something that you don't want in a concert hall. You want to avoid this as much as possible. And one way they avoid it is by having, instead of a single speaker on either side of the stage, you almost always have an array of speakers, 2 or 3 speakers. Even if it looks like there's only one speaker box, if you look inside that speaker box, usually there's at least 2 components inside that speaker. And that just kind of helps to even out this pattern. Because if you're in the spot of constructive interference for one of the speakers, if we have another pair of speakers, hopefully that are offset a little bit, maybe you'll be at a spot of destructive interference for those, and it'll kind of even it out. So this is one of the things that people talk about when they mention a room having good acoustics or not. So yeah, there's the picture from your book trying to show what I've drawn here on the board, and it does a much better job of showing the constructive interference here and the destructive interference here. Another example of interference is when you have two sources not separated by distance, but separated in time, essentially, separated in by frequency. If you have two sound sources, like two tuning forks, let me tilt this where you can see the tuning forks a little bit better. Here I've got the same two tuning forks I was using for some demos earlier, and they're both designed to produce the same frequency. So they're pretty close to each other, so when you hear the two tuning forks heard together, the sounds just blend very nicely. The two sound waves are in phase with each other, so you just get constant constructive interference. So when you hear one tuning fork, the addition of the second just makes it louder, okay? Just simple constructive interference. If I cause one of them to have a slightly different frequency by adding a little bit of weight to this tuning fork, now it's got a little bit more inertia, so it's going to vibrate a little slower, meaning its frequency is going to be a little bit lower. Now when the waves reach you, they won't be always in phase, right? Here's a diagram showing what is going to happen. So let me zoom in on that a little bit. So anyway, here you see the two individual waves. Here the light blue wave represents the higher frequency and shorter wavelength wave, while the kind of red wave represents the lower frequency, longer wavelength wave. So here you're seeing the two waves individually, and they start out in phase, but because their frequencies and wavelengths are a little bit different, by the time the second crest reaches you, they're offset a little bit. So the interference is completely constructive here, but here the interference is not perfectly constructive. They're a little bit out of phase. Then when the next wave comes, they're even further out of phase. When the next wave comes, they are completely out of phase. So at this point, the interference is completely destructive. Now, it doesn't take long for the waves to catch back up to each other. So as the waves continue, the crests get closer together, it gets closer and closer to being in phase again until they reach a point where they are back in phase. And then that process repeats, right? So again, they'll be out of phase. So if we look at the combined result, which is what you actually hear, the resultant wave, here where the interference is constructive, you have a louder sound. Here where the interference is destructive, you have a quieter sound. So it kind of alternates between constructive, destructive, constructive, destructive. So when you hear this, it causes the volume to rise and fall as you go back and forth between the constructive and destructive interference. This pattern of increasing and decreasing volume is called beats, and they occur with their own frequency. And that beat frequency is simply the difference of the two individual frequencies. That's probably the easiest physics equation you will ever see. So, for example, let's look at these two tuning forks again. So, one more time, here's what they sound like when they're at the same frequency. Just a nice, smooth sound. No beats, no alternating constructive and destructive interference. I'm going to add the weight to this one. So that's going to decrease this frequency a little bit. And do you hear that kind of wah, 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 wah sound? That's the beats. That's the increase and decrease in volume. If I change where I put this weight, that alters how different the frequencies are, and that alters the frequency of the beats. Here there's fewer beats per second, so the two tuning forks are closer together in their frequencies. If I move this down a little bit more, they're going to be even closer. So the beats are coming even slower. Right? Lower beat frequency, less of a difference between the two. If I put the mass here close to the end again, that makes the difference greater, so the beat frequency is greater. You can hear more beats per second. So one of the uses of beat frequencies is tuning musical instruments. That's in fact why tuning forks were invented. Let's put this back over here. That's why tuning forks were invented. You have a standard tone produced by a tuning fork. A tuning fork is designed to produce a specific frequency. So you strike the tuning fork, and then you hit the note on the piano or on the guitar or whatever, and listen. If the piano is producing the correct note, then you won't hear any beats. But if it's out of tune, then you'll hear beats. And that lets you know that you should adjust the piano, increase or decrease the tension of the strings until the beats go away. Another application of sound interference, not of beats, but just sound interference in general, is noise canceling. Noise canceling headphones are actually designed to reduce noise by making noise. It's pretty interesting how they work. Say that this is your head, and this is your ear on the side of your head. So here's your nose and your mouth and your eyeball. You're weird looking. I can't help it. I can't draw an eye. So anyway, if you have noise you would rather not be listening to, one way you can get rid of that is to wear a noise canceling headphone. Now what a noise canceling headphone does doesn't block the noise from reaching your ears. What it does is there's a microphone on the outside of the headphone that listens to the environmental noise you want to get rid of, and then on the inside of the headphone there's a little speaker that produces electronically replicated noise, but it's replicated in such a way that is 180 degrees out of phase from the incoming noise. So where the environmental noise reaches your ear as a crest, then the electronically reproduced noise is designed so that it reaches your ear as a trough, and that cancels that noise out. Okay? So they actually reduce noise by making it. And they actually work very well. All right, so here's a example using beats. This is extremely easy. A musician uses a standard 440 hertz tuning fork to tune a guitar string. When the string and the tuning fork are sounded together, 15 beats are heard over 5 seconds. What are the possible frequencies of the guitar string? We don't even need to write that out. This is easy. If you hear 15 beats over 5 seconds, that means you're hearing 3 beats per second. So the beat frequency is 3. That means that the two sounds that you're hearing together are 3 hertz apart. So you know that the tuning fork is producing 440 hertz. That means that the guitar string could be producing either 443 or 437 hertz. Those are the two possible answers. There's no way to know really which one just by listening to the beats. So if this guitar player were tuning his guitar using this tuning fork, then would increase the tension and see if that fixed it, if the beats went away, and if it didn't, if they got more pronounced, then you would just adjust it the other way until the beats disappeared.